Assalamualaikum warahmatullahi taala wabarakatuh, and a very good day to all of you. How are you today? So it's nice to meet you again virtually, right? So basically we will continue our lecture series on molecular and mixture design, and let's see where we are now in this chapter. So basically we have discussed about the framework, right, where we have 5 steps involving problem formulation, and then we have method selection and constraint selection, whereby we discuss about the knowledge base, about the translation of the problem formulation into measurable properties, and then in our previous lecture we discussed about the uh, molecular representation, right? And then how we can generate molecular structures and also mixture candidates, right, based on the molecular structures and the building blocks, right? So today in this video we'll be discussing about property prediction. Okay, so based on the molecules and mixtures which have been generated, so how we can predict the properties if we don't have the experimental values, or we don't have any known information on their properties. Then what we need to do is that we need to predict those properties using available what we call as property models. Okay. Okay, so for computer-aided molecular design problems, or computer-aided molecular blend or mixture blend design problem, so target properties usually include pure compound, and also as well as mixture properties. So these are the two main types of properties. We have pure compound properties, which is based on single compound, and then also mixture properties which is based on certain set of mixtures. Okay, and in order to be able to predict the target properties, we need to use what we call as property estimation model or property prediction models. Okay. So of course we need to do some literature search in order to find what are the available property prediction models based on certain target properties that we set. And of course, if we have the knowledge base, then of course in our database we should have the list of the property models, which we call it as property model library. Okay, so basically in that library you should find the list of properties that we can use, property models that we can use. Okay, so when selecting property estimation models, these are some of the issues which are related. The first one is on the in terms of the application ranges of the model, because certain models can only use for certain set or type of molecules, right? So that is with respect to application range, and then availability of parameters, right? For a certain property model, normally they would have a certain list of building blocks, whereby for certain building block or combination of building block, some parameters might not be available due to the lack of available experimental data needed in order to regress the parameters. So that one is on the development of the model, which we will not touch in this class. When talking about property prediction model, basically in this class we will just use whatever which are available. And the third issue is on the uncertainties. uh, Certain models, in terms of the estimation that they made, provide bigger uncertainties as compared to the other. Okay, it means that maybe the parameters are not that good, which means that the prediction also have some errors. So all right, so when talking about the application range, if our property model is limited in terms of what type of molecule that it can predict in terms of the properties, it will limit the size of the search space, right? Because well, when talking about the size of the search space, I think it would be better if we have a larger search space, because we will have a higher possibility of finding the most optimum molecules or mixtures, right? So the less the search space, then of course the less the opportunity for us to find the most optimal uh, uh, chemical molecules or mixtures, right? Okay, so if parameters are not available, if let's say for certain compound that we are interested in, for example, that compound maybe need to use the group COO, for example. I'm just giving an example. So let's say for certain for COO, maybe for example the parameters are not available. So if it is not available, then we cannot use that model in order to predict that particular compound. Okay, so related molecules and mixtures must be removed from the list of the candidates. Why? Because we don't have the needed parameters that we can use in order to predict its properties. Then if we remove it just because of that, then we will eliminate we might eliminate potential optimal products, eh? Because the candidates that we remove might have better performance, maybe, as compared to the available, to the candidates whereby we have the parameters, right? It can be a possibility, right? So since we don't have the needed parameters, so then it need to be excluded. And if it has a potential, then we are eliminating potential um optimal products, right? Okay, so our intention is to have a model with fewer parameters, but with a larger application range. Okay, so when talking about parameters, because in this class, what the types of parameters that we use is based on building blocks, whereby molecules are uh, uh, what you call it, disassembled into smaller fragments, right? So when it is disassembled into a smaller fragments, then the parameters will be more. If let's say if we consider parameters for molecules, right? So then, but of course, if we have parameters for groups, for molecules, then the application range will be lower, because if we have parameters based on molecules, then the only um, system that we can predict using the model is based on that particular molecule, right? So if our parameters is based on functional groups, okay, because when talking about functional groups such as CH3, OH, CH2, CH2O, for example, those are example of functional groups, right? So if we consider parameters based on functional groups, then we might have a larger possibility of the type of molecules that it can form, right? Whenever you add certain functional groups, right? So basically, it's like a Lego, right? So if you have more blocks of Legos, or smaller blocks of Legos, you can build many more different structure, for example, right? Rather than having a big block of Lego, and then you want to build different structures, right? So it would be less compared to when you have smaller parts, right? So basically we need to have a trade-off, right, in terms of the fewer parameters and as compared to larger application range. Okay, so in terms of the estimation task, because for a certain product design problem, computer-aided molecular design problem, we need to predict many different properties, right? Based on, of course, based on the needs, right? I'm sure you already noticed this, that for a certain problem formulation, for certain needs, there can be many different properties which are needed, right? in order for us to come out or generate the products, chemical product which satisfy the needs, right? So of course, in order to perform the estimation, we cannot do it all at once. Okay, so we need to do it systematically. So the way that we can do is by arranging the estimation task hierarchically, based on the computational effort and also cost. Okay, so this is an example of the distribution of the properties according to the hierarchy. So we have hierarchy number 1, 2, 3, and 4 here, and then for each hierarchy we can see that there are different property types. Okay, we have primary property, secondary property, functional, and also finally mixtures, and all these are examples of the properties related to each category, property type, and also here listed the calculation method. So basically, whenever we need to do property prediction of all the target properties that we have translated from the problem formulation. So first of all, what we need to do is that we need to do prediction for the primary property first. Later on, I think I have briefly explained what are the meaning of each of these types of properties, right? But later on there will be a revision on that where we will discuss further on what is meant by primary property, secondary, functional, and mixture. But so basically, this is the step that we need to go through whenever we need to do the estimation task. So we start with the primary properties first, and then we move on to the secondary properties, and then functional properties, and then finally mixture properties. So each of these properties have their difference in terms of the computational effort and also the related cost. Okay, so the cost means here is in terms of the computational cost. Okay, all right. So basically, by doing this is that we perform the computational intensive calculation only for candidates which satisfies all the targets using simpler property model. So normally the property models for the primary is simpler compared to the secondary, simpler compared to the functional properties, and simpler compared to the mixture properties. So normally for the prediction for mixture property would be the most complex one. So if let's say, for example, if let's say you have like 1,000 candidates, right? So and then of course based on our target properties, there's a certain goal or range whereby we want the target properties to have in terms of the values. So it means that, for example, if let's say let's say our target property is normal boiling point, right? So let's say we have 1,000 candidates. Okay, so let's say in terms of our requirement, we want our candidates to be liquid at room temperature, for example, right? So the properties which we want to measure is the normal boiling point and also the normal boiling point, right? So we want to make sure that uh, the these two values can contain the room temperature, which is 22 degrees Celsius. It means that the boiling point must be higher than the room temperature. The normal melting point must be lower than the room temperature. We need to make sure that. Okay, so in order to check that, then of course for that 1,000 candidates, we estimate the properties of these two properties lah, boiling point and melting point. So from that 1,000 candidates, so only those candidates whereby their boiling point is higher than the room temperature and melting point is lower than the room temperature will only be chosen. Okay, so those properties, for those candidates whereby, for example, maybe the boiling point, the melting point is higher than the room temperature, then of course it will not be chosen, right? Okay, so only candidates which satisfies the constraint, the goal value will only be chosen, right? So basically for hierarchy number one, so we need to do 1,000 of predictions because we have 1,000 components, right? Compounds. And then by comparing the values, predicted values with the value goal or the constraint, then we can exclude those which are not satisfying the constraint, right? So maybe from 1,000, then you get 500, for example, right? Then if there is a secondary properties that we need to estimate, so we just need to estimate for the 500 candidates. So we have a lesser amount of candidates with a higher complexity of the model or method, right? So let's say from the second hierarchy, we do the prediction for 500 compounds, and then maybe half of it does not satisfy the constraint. Then it leaves us with 250, right? So when we move on to the third hierarchy, then we only have 250, for example, whereby we need to predict maybe their vapor pressure, for example. Okay, and then as usual, when it does not satisfy a certain constraint that we set, then maybe half of it will be removed, and then maybe for the fourth hierarchy, we only have like 100 candidates, for example, from 1,000, for example. So since for mixture, the calculation is more complex, is involve non-linear, mainly non-linear equations, right? So we only need to perform this computational intensive calculation for 100 compounds rather than 1,000 compounds. Because if you need to calculate for 1,000 compound using a more complex equation, then it would take some time for you to get the estimation, right? Whereby it may not be necessary, because if we do it hierarchically, okay, we can remove a lot of candidates which does not satisfy the primary, secondary, and functional properties, right? So then for mixture, we only need to do it for 100, right? So by doing that way, by doing hierarchically, in terms of the estimation task, we can remove those candidates, and we can only focus we can remove those candidates which does not satisfy the constraint, and we can focus the computationally intensive calculation only for those candidates which have satisfied all the previous constraint. Okay, so that is why it is important for us to do this way of to estimate to perform the task hierarchically lah. Okay. Okay, so basically this is maybe a revision of what we have discussed before. So properties basically can be divided into several classification, several type. And whereby the first one we have okay, so primary properties is a single value properties which can be calculated based on only the structural information of the molecule. Okay, so that is primary properties. So for secondary properties, in addition to the structural information of the molecule, it is also usually a function of other properties, as normally the primary properties. Okay, so secondary properties is a function of the primary properties. So in order to calculate secondary properties, first of all, we need to predict the primary properties first. Okay. So and then we have functional properties. So basically this is pure compound properties that depends on the intensive variable, namely temperature and or pressure. Okay, so that is functional properties. And then we have mixture properties. So in addition to its structural information, mixture property also depends on the intensive variables, temperature, pressure, and of course composition. Okay, so from this figure, we can see the relationships among properties, property models, solvers, and also calculation algorithm. Okay, for example, in order to estimate properties, so let's say this is our properties. So in order to estimate these properties, we need to select the properties, property model first. You can get it from literature search, or you can get it from your knowledge base, right? And then of course you calculate the properties. Okay, and for phase equilibrium related mixture properties, okay, like this one, VLE, LLE, and SLE. I'm sure as VLE you have learned it in your chemical engineering thermodynamics, right? So that is our focus in that course on VLE. And of course, you can also, if you know VLE, then I'm sure it would be easy for you to understand LLE and also SLE. Okay, so in order to solve this problem for phase equilibrium, so we need to have a solution algorithm employed and that require estimate of other properties. So we need to have this algorithm or numerical solvers. Okay, right? So then only we can so using this numerical solver, so we need to have an algorithm for that so that we can calculate whatever needed phase behavior. Okay, so required properties estimate, required property estimate ordered, to be ordered and calculated according to the hierarchy lah. Sebab kita dah dalam mixture kan, so of course you may need information on the primary properties, secondary properties, functional, then only at the end you will be able to calculate the properties of the mixture.